exam 1 review for EE 2950. We're going to start with some concepts, and we're going to work about 9 to 10 problems to review for the exam. Okay, so going through the concepts, we're going to start with our favorite equation, Ohm's law, which is V is equal to I R. Our power equation is going to be P is equal to V I, which is also equal to V squared over R, which is also equal to I squared times R. Remember, if we have positive, it's going to absorb. If it's negative, we're going to supply. Looking at the KCL is going to imply there's a node. And what we're going to do is look at the currents that are going in and out. I1, I2, and I3. We say that we can sum the currents to equal 0. So that means that the currents that are entering are going to equal the currents that are exiting. Okay. So we can write one of two things. We can either write I1 plus I2 is equal to I3, or we can write plus I1 plus I2 minus I3 is equal to 0. And we can actually write it a third way. We can write minus I1 minus I2 plus I3. All three of these are just the same exact equation, just rearranged in different ways. Okay, so then we'll move on to the KVL. So KVL is going to imply loops, and that looks like this, in the sense that we have a voltage source, we have a few resistors where we know the terminals and the source voltage here, where this is voltage 1, this will be voltage 2, and then this will be voltage 3. And just like the KCL, we're going to sum the voltages to equal 0. And we'll pick a point and walk along this loop with our current. And every value we hit with our current is the value we're going to apply to the voltage. So we'll hit negative V of S, we'll hit positive V1, we'll hit positive V2, and we'll hit positive V3. We'll end up back where we start, and we can set that equal to 0. And then oftentimes when we're doing these, we're going to end up replacing V with equal to IR. Okay, looking at series and parallel resistor combinations. So series are going to be on the same wire. And remember, these cannot cross a node. And our equation for the R series is just the sum of the resistors on that wire. So R1 plus R2 plus R3 plus ... And really quickly, we were to draw out 2 quick examples. All right. The one on the left is in series because they are on the same continuous wire. However, the one on the right is not in series because you have these 2 nodes here, and you have that resistor that's messing it up. Okay, so we can't take this node and slide it that way, and we can't take that node or that resistor and this resistor and slide them that way, and we can't slide that resistor that way because we can't cross over that point. Okay, if we look at the parallel, we can say 1 over R parallel is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot dot dot. You can simplify this a little bit and say R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot dot dot. And if we were to draw out a couple examples, all right, and if we take a look at these here, we can see that the one on the left is going to be in parallel because there's nothing in between these branches. It's just the 3 branches there are in parallel with each other. Nothing in between them. But this one over here is not going to be in parallel because we have those resistors that are blocking it. Okay, so because there's something between these points, we're not in parallel yet. Okay, if we come look at a voltage division, this is going to require that we have a loop. And if we wanted to find voltage across a specific resistor, like this, R1, R2, R3, and then this will be via the source. If we wanted to find the voltage across the first resistor, so V1, that would be equal to R1 over R equivalent times V of S, where R equivalent here is going to be equal to the series. So therefore, V of 1 is going to be R1 over R1 plus R2 plus R3 times V of S, where the denominator here is just R of S. Okay, and if we look at a current division, we see there's a similar thing. We're going to need parallel branches. So say we have something like this, and we know we have a current I of S going that way, and we want to know the current I1 that goes down this way. If we look at our equation, if we want to find I1, it's going to be R1, where this is R1, over R equivalent times IS, where this is just R1 over R parallel times I of S. Okay, now what parallel are we going to use? Well, since our current that we're breaking up, IS, is way over here, and it's before we hit any of these resistors, our parallel is going to be all of these. If we do the something different, like this, this will be R1. where we know our I source is coming this way, and we want to find this I1 now. Now, this is our R parallel, okay? It's the only resistors that are involved with the current that's being broken up. So you can see that the current is being broken up here, so we need to include all of these resistors. But if you look here, it's only being broken up across these two. So you're only going to use those two. All right, and then a small tip, if you can't remember these equations, which value goes on top, the smaller value goes on top. Okay, so that would be the R1 and R1. Actually, my mistake here. This should be R equivalent over R1, R equivalent over R1. There we are. Okay. Moving on to the nodal analysis. So as the name implies, we need a node, and it's going to be assumed in this method. We're going to assume all currents leave except for known current directions. Okay. So what this does for us is, if we have a node, we're going to assume that all of our currents at a point, I1, this will be I2, and this will be I3, they're all going to be exiting. And if I was to go and draw this out just really quickly, so call that one V of A, call this point V of B, call this point VC. And we'll have R1, this will be R2, and this will be R3. Okay, so something that we have to have for a nodal analysis is a thing called a ground. And what the ground gives us is a point of reference. And what we want to do is to select a point that will help us out the most. So if we look at the bottom wire here, you see that there's a point that all three of these wires connect to. So if we go and drop our ground down here, where there's 0 volts, we now have a point of relation for all three of these branches. So it's very helpful for us. And what we'll do is we'll assume that all of our currents are going out of this point. So how do we write the equation? So we can say from KCL, I1 plus I2 plus I3 is equal to 0, because they're all exiting. And what we'll do is, in the nodal analysis, we'll replace I with V of start minus V of end over whatever resistor we cross over. Okay, so if I took this I1 here, I'll write it out. So I can say I1 would be V of B minus V of A over R1. And then I can come over here and look at R2 or I2 and say V of B minus V of C over R2, because we're going from B to C. Start minus finish. And then we can say we're going from B to V of G. So V of B minus V of G over R3 is equal to 0. And the good thing is that we know what V of G is, so we can just go ahead and set that to 0. And what you'll end up doing with this is just, if it's more than one point, you'll end up solving a system of equations. Okay, let's take a look at the mesh loop analysis. So mesh loop analysis, we do loops. We'll do something like this. Plus minus R3, R2, then R1. All right, and what we're going to do is we're going to, this is a similar type problem to find currents or voltage points at nodes. So what we'll do is we'll say, I see that we have two loops here, so I will go ahead and draw those loops out. And I'll say this is V of A and this will be V of B. And I'll do my KVL equations. So I can write out for KVL, this will be loop 1, this will be loop 2. So for my KVL equations, like I said, I'll pick a point and walk around. So minus V of A plus I1 times R1 plus, now this is R3, right? Because we're going down the middle branch. Now we're going with I1 and I2 as well, okay? Because now what we're doing with this is we're saying I1 and I2 are meeting up to form this new value called I3. So this value here is I of 3. So I can write up here I of 3 is equal to I of 1 plus I of 2. That's what we're assuming. And what we're going to do is work out the system of equations to see if our assumptions were right. Okay, we'll end up back at 0. So this was loop 1. If we come and write loop 2, we'll do something similar. We'll walk around. I2 times R1 plus R3, I1 plus I2 will be equal to 0. Okay, and so this will be our first equation, this will be our second equation. And you're just going to solve the system of equations from there. And there's a few methods to solve systems of equations. You can do plug and chug, or you can do Cramer's rule. And Cramer's rule, if we were to go and write our equations out, I'll just say ax plus by is equal to z1, then cx plus dy is equal to z2. And something we need to know is the determinant. What a determinant is, it's a, b, c, d. And this will be AD minus BC. Okay, that's a determinant value. So if we wanted to solve for the value x, we can come up here and say the determinant of, so this is the X column here. This is the Y column. We can see because they're stacked on top of each other, this is X and that's Y. So if we're solving for X, we'll replace the X column with our knowns column, Z1, Z2, and then we're going to leave the Y column alone. And then down in the denominator, what we're going to do is we're just going to keep the X and Y columns the same. So this will be A, C, and this will be B, and then D. And what this will end up being is Z1 times D minus B times Z2 over AD minus BC. Then down here, if we want to solve for Y, we'll leave the X column alone, and we'll come in here and replace the Y column with the knowns. And then in the denominator, we'll do the same thing that we did before with the denominator. So now this will be A Z2 minus C Z1 over AD minus BC. All right, and I believe that is it for the concepts. I will see you in the problem solving section.